All right, what's up? It's time to do another one of these research videos. For this one, I actually don't have a topic selected. So what I'm going to do is I'm actually going to use Bing AI to give me a random topic to research. And I'm going to use it to pull like a whole list of topics, and I'll see which one sounds the most interesting, and we'll go from there. Let's see. So yeah, I have Bing AI pulled up here. I wrote out this prompt that I'll paste in here. Filming a video in which I research a topic for 20 minutes, then speak about what I've learned for 5 minutes. Can you give me a few random topics to research? So let's see if it has any interesting suggestions. Okay, quantum computing, conspiracy theory, psychology, space exploration, colonization. Okay, these are interesting, but they might be too broad. Okay, honestly, the quantum computing one, maybe I could do this because we hear about this term a lot, and I've also heard that it's going to be big in the future. But to be honest, I just know some of the basics of quantum computing, and maybe it would be interesting to get a better idea of what exactly it's about. Yeah, I think we're ready to begin. 3, 2, 1. Let's go. Okay, so the first thing we always want to do is plan out what this is going to look like, right? So what exactly are we going to research? Quantum computing. First of all, we want an overview / introduction. And this is going to include things like what exactly is quantum computing on a basic level. And then as part of this, I think, or as a follow-up to this, we're going to contrast this with regular computing. I know a little bit about this, so I'm coming in with a bit of prerequisite knowledge, but I really honestly just know some of the basics. So don't know much more than that. Maybe what are its benefits? Maybe more broadly, why is it promising as a technology? Okay, that can be one section. Maybe another section can be some of the history of quantum computing. I mean, I'm guessing it doesn't have a very long history, right? But we can talk about stuff like early breakthroughs in quantum computing. That can come in a lot of different forms, but I'm guessing you're probably going to see like inventions from companies or like research papers 20, 30, 40 years ago talking about the potential of quantum computing. So early breakthroughs in quantum computing is important. And then after that, we probably want to lead it up to the modern day and it's like get a good idea of what it's like, what the current landscape is like for quantum computing. So regarding that, I'll say biggest players in quantum computing, maybe. Yeah. Okay. And then, maybe also at the end of this, we'll talk about future potential things to look forward to. Okay. I don't know if we need another section right now. Maybe we will, but for now, I think I'll start just using all of this. So to start with, what exactly is quantum computing on a basic level? Let's pull up, I mean, you can never go wrong just searching the thing up on Google, right? Or on Bing. It's interesting to know that the first result that shows up is actually this IBM result. So I'll probably put IBM under biggest players, and we can learn more about that in the future. Learn quantum computing. Oh, this is an ad. Okay, this is an ad, but still, it seems, I mean, we know IBM is a big company, and they're probably investing into quantum computing if they have this ad up here, right? So that's good to know. The thing is, for topics like this, I don't want really to go into the Wikipedia too much. We can open it, but the problem is with like hardcore physics or math related topics, they usually get into really rigorous notation that is really hard to read if you're not familiar with that subject area. So what I'll go into is maybe something like this, this MIT Technology Review or Wired. They'll dumb it down a bit, you could say. What is this Google Quantum AI? I'll just open this up to take a look quickly. Okay, this is going to be a little bit inefficient, I think. Maybe we can find something else though. Okay, NASA, this could be good. I'll start with this NASA one actually. Okay, no, this is like written like an article. So actually I want something else that's like a little bit more structured in terms of the way that it's written. This one I need a subscription to read. Perfect, amazing. This one, MIT Technology Review, let's see. Okay, this is, yeah, I think this is decent. Let's see. Wait, let me just go to the Wikipedia first and see if there's anything immediately that we can get from this. Yeah, see, this is what I meant. Like, they have a lot of math here, and I don't really want to get into interpreting this because that'll end up taking a lot of time. So I'll rely on this for now, on MIT Technology Review. So what is a qubit? Yeah, okay. Here's the biggest thing. So quantum computing on a basic level. Here you can see they say today's computers use bits, and quantum computers, on the other hand, use qubits. Bits are a stream of electrical or optical pulses representing ones or zeros, and qubits are subatomic particles like electrons or photons. So, okay, if I had to summarize this, it's basically saying that quantum computers use subatomic particles to represent data rather than electrical impulses. So, and rather than digital electrical impulses, right? So it's saying that in a normal computer, and this is contrasted with the regular computing, I'll put it under here. Normal computers have regular bits that represent ones and zeros, on and off. And then they're saying that if you look here further down, qubits have some quirky quantum properties. I mean, a connected group of them can provide way more processing power than the same number of binary bits. One of these properties is known as superposition. Another is called entanglement. So down here under what is superposition, qubits can represent numerous possible combinations of 1 and 0 at the same time. Yeah, exactly. This ability to simultaneously be in multiple states is called superposition. Okay, I'll write about this over here. So normal computers have regular bits represent ones and zeros. In contrast, what you see with quantum computing, qubits, they're called qubits, which are able to encode much more than 2 possible states into each individual unit. And the reason why they're able to do that is because qubits can be in quantum superpositions, meaning they can be in some intermediate combination of 1 and 0 at the same time. This is like one way to think about it. I don't know if this is literally how it works, but essentially instead of being a 1 or a 0, a qubit can be like 70% 1 and 30% 0 or something like that, essentially. So because of that, it opens up a way wider range of possible states for qubits to be in. Okay, anything else that I want to include here? Oh, okay, wait, one more thing I want to write here. It says, to put qubits into superposition, researchers manipulate them using precision lasers or microwave beams. So halfway through the time, I think it's okay for now. Thanks to this counterintuitive phenomenon, a quantum computer with several qubits in superposition can crunch through a vast number of potential outcomes simultaneously. The final result of a calculation emerges only once the qubits are measured, which immediately causes their quantum state to collapse to either 1 or 0. So, I mean, I'm going to draw upon a little bit of quantum physics knowledge, like basic quantum physics knowledge that I have, which is that when you have a superposition, when you have any superposition, a superposition collapses to like once the state of that superposition is measured. This is called the measurement problem in quantum physics. And what that means is with qubits in particular, qubits resolve to 1 or 0 when they are measured. So if I had to intuitively make a guess about the implication here, it's suggesting that while these qubits are in superposition, they can perform kind of like several roles at once. They can do multiple calculations simultaneously, as this MIT article says over here. And then once they're actually measured, then the calculations are resolved. Okay, interesting. I always get obsessed with the formatting, even though it probably doesn't matter this much. Okay, anything else? So this entanglement as well, they mentioned this was an important thing. Yeah, I know that basically quantum particles can get entangled. They're saying, yeah, pairs of qubits can be entangled when researchers generate them. Two members of a pair exist in a single quantum state. Makes sense, yeah. Changing the state of one of the qubits instantly changes the state of the other one. So yeah, I mean, I'm not going to go into entanglement right now, hardcore, but let's see how this is relevant to quantum computing. So quantum computers harness entangled qubits in a kind of quantum daisy chain to work their magic. Machines' ability to speed up calculations using specially designed quantum algorithms is why there's so much buzz. So that's the good news. Bad news, quantum machines are way more error prone. Okay, we'll get into that later. But basically, qubits can be entangled when generated, allowing researchers to speed up calculations using algorithms to daisy chain, I guess, qubits. So when you affect one of them, you can potentially affect like a whole bunch of qubits at the same time. That's what it's saying. So, okay, under benefits, I'm just going to refer to / repeat stuff above. I'm not going to go into a whole lot of detail because we are kind of running out of time here. But I do see that there is this decoherent section that maybe we want to write about. This is kind of a drawback. So I'm going to write about that here. Decoherence. Why is this bad? So interactions of qubits with their environment the interaction of qubits with their environment in ways that cause their quantum behavior to decay and ultimately disappear is called decoherence. A quantum state is extremely fragile. The slightest vibration or change in temperature can cause them to tumble out of superposition before their job has been properly done. This is why researchers do their best to protect qubits from the outside world in these supercooled fridges and vacuum chambers. The noise still causes a lot of error to creep into calculations. Okay, take thousands of standard qubits to create a single highly reliable one. So they haven't been able to generate more than 128 standard qubits. Okay. We're still many years away from getting quantum computers that will be broadly useful. Okay, so what I'll just say here is that quantum states are very sensitive to their environment. So they must be stored in highly protective facilities, I guess. And even then, there are errors that arise from noise in quantum computer calculations that researchers must deal with. Okay, so this is basically one of the main challenges of quantum computing, and I'll talk about this a little bit. Now, history of quantum computing, let's see. Wait, what is quantum supremacy here? It's the point at which a quantum computer can complete a mathematical calculation demonstrably beyond the reach of even the most powerful supercomputer. Okay. I don't need to go too much into that. I do see them listing companies here, though. Wait for supremacy. Companies starting experiment with quantum computers made by companies like IBM, Rigetti, and D-Wave, Canadian firm. Okay, so Rigetti and D-Wave and that's it. So these are maybe some important players. Early breakthroughs. Okay, wait one sec. We are kind of short. We're kind of short here. Any breakthroughs over here? There probably is a little bit over here. It says 1972 parallel computer. I don't know. Let's see. Quantum computing breakthroughs timeline. I want to see if I can get like an infographic about this somehow, which would be perfect. Theoretical foundations of quantum computing. Yeah, we don't need to go through that. Feynman's quantum computer proposal. Okay, 1981. Maybe I'll just do something like this. So 1981, Richard Feynman, he was a big, well-renowned physicist. He maybe proposed quantum computing. We can verify that quickly. 1981, Feynman quantum computer. Oh man, I don't know. I don't want to like just put that down and take it for granted, right? Okay, basically, maybe I'll keep this very broad. Like we'll just put down saying that we'll put down this idea that through the 1980s and we developed protocol theories that would be applied later in quantum computing. I have to kind of shorthand stuff now. In the 90s, they started developing quantum computing, like actually physically. 1990s, we developed the first quantum computers and algorithms. Okay, and then after that, there's been a rise basically since the mid 2000s, it seems like. And Microsoft got into it, Google as well. IonQ, I actually know about IonQ. Yeah, this is a very recent one. So maybe I'll also put these down. Microsoft, Google, and then IonQ. Future potential things to look for. Okay, yeah, and then here maybe I'll put quantum supremacy, actually. Oh, okay, I didn't realize there's a whole article here. Maybe I could verify over here. Richard Feynman's vision, yeah, a physicist, he delivered a similar lecture. Computer operating quantum principles, yeah, okay, so it was, I'll mention this then, because he is a big name, so I do want to include his contribution. And then we have these two algorithms. A quantum algorithm, now known as Schwartz algorithm, leverages the principles of quantum mechanics to efficiently factorize large numbers. Okay, it would take exponentially longer on classical computers. Okay, so maybe I'll write that as an example of something that was important. So I'll say Shor's algorithm, factorizing numbers much, much faster than on regular computers. Okay, this might be enough. I think for 5 minutes, I'm gonna stop researching now, and we'll shift over to the other setup. Okay, I'm ready to go now. We have a decent amount down, I think. Obviously we can always do more, and I'll get better at researching too. But for now, I think I did learn something. So let's get to talking. 3, 2, 1. All right, let's begin. Okay, so I looked into quantum computing for 20 minutes, and this is what I learned. First of all, looked into what quantum computing is on the most basic level, how the technology works, how it is contrasted with regular forms of computing or classical traditional forms of computing, and why it could be promising, as well as what some of the challenges are that we're facing right now with quantum computing. And just to begin with, quantum computing on the most basic level is basically the application of subatomic particles and quantum physics to represent data rather than using digital electrical impulse. Now, the reason why that is so different and revolutionary is because normal computers have regular bits that represent ones and zeros, which means that maybe like a particular transistor on a chip is either on or off, represented by the 1 or the 0, right? Those bits can either be 1 or 0, and obviously not both at the same time. That wouldn't even make logical sense, right? They have to be either on or off at any given point in time. They can obviously switch between those two phases, but they have to be one or the other. Quantum computers, they use this other type of technology called qubit. So instead of using electrical impulses, they use subatomic particles to represent the data that they're calculating, that they're using for their calculations, right? And one feature of subatomic particles is that they can be in superpositions, meaning that rather than being in one state or the other, they can be in a hybrid state. So those qubits, by virtue of the fact that they can be in a hybrid state, they can encode much more information at one time being in a superposition than a regular bit would be able to. So if we compare it to regular bits, qubits might be, for example, like 70% 1 and 30% 0 at any given point in time. And researchers using quantum computers, they can manipulate these qubits, change their superpositions using hyper specific precision lasers or microwave beams. And another feature of superpositions in quantum physics is that once they're measured, they actually collapse. Like that superposition collapses so that you actually do end up measuring, when you actually measure these systems, you end up measuring a 1 or a 0 rather than this hybrid position. So until you've performed that measurement, the quantum state is in a superposition, and then afterwards it collapses into a 1 or a 0. So the interesting thing about that is that means that quantum computers, while the qubits in a quantum computer are in a superposition, they can handle like a huge number of tasks all at once, potentially. And then when you actually measure those qubits, you can resolve the calculations that you're performing so that you get like the answers to all the calculations, I guess, that you were performing at the beginning, right? So why is quantum computing beneficial? I mean, through the superposition thing that I mentioned, you can kind of understand that for certain tasks, quantum computing can be far more exponentially more quick than regular computing. And actually quantum particles, subatomic particles, can also be entangled, meaning that researchers can generate qubits that are entangled, and whatever they do to one particle would do something predictably to the other entangled particle as well, which speeds this process up even more. At the same time, it is important to know that quantum computing has this problem of decoherence, meaning that there's a lot of noise that can affect the sensitivity of these quantum states, and researchers have to find a way to deal with that before they become actually practical. Like in terms of a brief history of quantum computing, through the 80s, there was a lot of proposed theorizing about quantum computing, especially from renowned physicists like Richard Feynman. In the 90s, we developed the first quantum computers and algorithms like Shor's algorithm, which showed that it can be exponentially faster for certain tasks. And now we're into the phase where companies like IBM, Rigetti, D-Wave, Microsoft, Google, and IonQ are actually experimenting with quantum computing practically. Okay, I just barely got to the end there. I didn't include quantum supremacy, but that's not the most important point. So you know what? I think I'm fine with that. I think I'll leave it there. Yeah, I think that was decent. And yeah, let me know if you think you have any suggestions for any topics or anything that I should do in the future. But apart from that, thanks for watching. See you later.